Hi, Steve Ellingson here with a lecture on amplitude modulation. Amplitude modulation is a form of sinusoidal carrier modulation, and by that we mean modulations which send information by manipulating either magnitude, frequency, or phase of the waveform. In the case of AM, we send information by manipulating the magnitude of the carrier. So the idea is this: if we have a message waveform, depicted here as this curve, time domain waveform, then what we do is we use that waveform to manipulate the magnitude, or as we sometimes say, the envelope of the carrier. So an unmodulated carrier would be simply a sinusoid, but we send information by changing the magnitude of the sinusoid with time. It's useful to understand the spectra of these signals. So what I've done here is I've depicted the spectrum of the message waveform. That's the frequency axis that I've highlighted here. And this waveform can really be anything that occupies a specified bandwidth. I'm depicting that generically here as this spectrum, this power spectrum. Of course, you should know that any real-valued waveform in the time domain yields conjugate symmetric spectrum. So we don't get simply the positive frequencies, we get the negative frequencies, and specifically we get a spectrally reversed copy of the positive frequencies. So we refer to this as being a conjugate symmetric spectrum. What happens in AM is we're simply taking that spectrum and shifting it up to the carrier frequency, F sub C. So we get the exact same spectrum, except now shifted by that much, with one additional issue. We also see the carrier appears as part of the spectrum. So that's a feature of many forms of amplitude modulation. That simply reflects the fact that the envelope here has a DC value which is other than 0. So we see that as a line at this carrier frequency. Of course, something else to know about AM is if you've filled up a bandwidth of W in the message waveform, then what will happen is the bandwidth of your RF waveform will be twice W, 2 times W. And we'll come back to that idea a little bit later. So this is a common form of amplitude modulation known as double sideband large carrier. And people use different acronyms for this, but generally DSB and then sometimes the -LC to indicate that the carrier is still present. Typically the waveform, the message waveform in AM, the A of T, is audio voice. That's not the only possibility, but that accounts for many, perhaps most AM applications. Moreover, we're typically talking about low fidelity voice, that is just frequencies below 3 kilohertz or so. So if the message bandwidth is 3 kilohertz, then the RF bandwidth is about 6 kilohertz. And you should probably know that the spacing in the RF domain is typically 10 kilohertz. That allows a couple kilohertz on each side of the message waveform so that there is no interference between adjacent signals. Here are a few common double sideband large carrier AM audio systems. Of course, the one that might come to mind right away is AM broadcast. There is a band of frequencies that go from 500 to 1800 kilohertz. That's known as the medium frequency spectrum. And these are AM radio stations, the ones that appear on your car radio. Another common double sideband large carrier audio system is Citizens Band. This is 40 10 kilohertz channels, around 27 megahertz or so. That's the HF spectrum. So Citizens Band is most commonly associated with truckers, but a lot of folks use this. Yet another double sideband audio system that you should probably know about is airband, referring to aviation. So these are communications, for example, between aircraft and the airports at which they're taking off from or landing at. Also international. So those international communications between, say, air traffic control and passenger jetliners, where the jetliner is perhaps approaching from the Atlantic, approaching North America, those communications are typically done using double sideband large carrier in the HF band. The airport operations, those are short-range communications between aircraft coming and going from an airport. Those are typically VHF. Those occur in the band 118 to 137 megahertz, which is VHF. So, two things you should know about double sideband large carrier AM. First is there is no information in the carrier, yet the carrier contains a big fraction of the power. Just go back and look at this picture. Remember I pointed out that there's a ton of power right there. And that power is not sending any information. However, this carrier is necessary for receivers using envelope detection. So perhaps you already know about envelope detection. That's merely detecting the magnitude of the signal, typically using some form of rectification. These days, it's less important because many, perhaps most receivers that are receiving AM are digitizing receivers, so there's a number of other options besides envelope detection. So with this in mind, frequently new or newer AM systems use a scheme known as a suppressed carrier, sometimes abbreviated DSB-SC for suppressed carrier. In that case, we're getting rid of the carrier, and we end up, in fact, with spectrum that looks like this, so the carrier is missing. That is much more power efficient because you're not sending that carrier, which has power in it, but is not conveying any information. The second issue you should know about double sideband large carrier systems is that the spectrum consists of two sidebands. I pointed this out. In fact, even double sideband suppressed carrier has these two sidebands. And they're conjugate symmetric, which means they're redundant. You have the same information in both of these sidebands. So you really don't need to send both, and the bandwidth is twice as large as necessary. So this results in a condition that we refer to as low spectral efficiency. Spectral efficiency is the ratio of information to the bandwidth used to send that information. So typically, we want the spectral efficiency to be high. That is, we want to send as much information as possible in as small a bandwidth as possible so as to conserve bandwidth. So the improvement is single sideband. That is only to send one of these two sidebands. Single sideband, or SSB, comes in two flavors depending on which sideband you intend to send. If you just send the lower sideband, that's referred to as LSB, or simply lower sideband. If you intend to send just the upper sideband, that's USB, and you get this. So you see right away that these two forms of single sideband have half the bandwidth of a double sideband system. And so it's more spectrally efficient, and that's the most common reason for seeking out this form of modulation. I should point out that single sideband in either flavor is very popular for voice communication in the HF spectrum. And the reason is because in the HF spectrum, from 3 to 30 megahertz, spectrum is severely limited. There's very little space remaining to operate communication systems. A downside of single sideband is that the receivers are a little more complicated. Not dramatically so, but envelope detection is out, that's for sure. And you need to have a scheme that does not require the carrier to be present in the signal. Furthermore, a single sideband receiver needs to restore that missing sideband to get back the original message signal. So these are things which makes SSB a little bit more complicated, but not dramatically so. Another important form of AM is continuous wave. So first let me warn you that the term continuous wave gets used with a couple different meanings, and so be aware of that. Here when I'm referring to continuous wave, I'm referring to continuous wave in the context of amplitude modulation. So what we mean by continuous wave here is that there are only two possible states of the message signal, namely on and off. So it's either on or off, so on. So fully on or fully off. Some people might be tempted to refer to this as a digital modulation, but that's not necessarily the case. Typically when we say digital, we would mean two defined symbol waveforms. In other words, it might be off for a certain amount of time and on for the same amount of time. Those would be two states. That would be amplitude shift keying. So for example, Morse code, an A is, we say, a dot and then a dash. So the message waveform looks like this. A B is sent as a dash followed by 3 dots. You should know that Morse code is actually pretty popular at HF, and the reason is because it can have extraordinarily small bandwidth, typically less than 500 hertz or so. Actually, often much less than 500 hertz or so. And it has the advantage of being very easy to discern in the presence of noise and interference. So what that means is when there is noise and interference in the channel, they of course interfere with your ability to demodulate, but CW, you're only listening for 2 things. Is it present or is it absent? And those things are relatively easy to discern compared to a continuously varying waveform. So Morse code-based CW AM communication is quite popular in these applications where you need extraordinarily small bandwidth and you need to be able to work in the presence of noise and interference. Another type of CW AM system is a pulse radar. A pulse radar is a type of radar that sends millions of CW pulses per second. Typically, the bandwidth in that case ends up being on the order of megahertz. So an example would be L-band long-range air traffic control radar. So there's a network of these radars in the United States and in fact in every country that determine the locations of aircraft so as to facilitate air traffic control. And these are typically pulse radars. In other words, they're sending these CW pulses. Now, again, the term CW gets used to mean a couple different things, and confusingly, CW radar is different from pulse radar. CW radar typically refers to either Doppler radar or a mode of radar known as FMCW, frequency modulated CW, and those are not AM. So just to be clear, it's only pulse radar that has this AM type of modulation. In either case, the spectrum of CW modulation, that is the pulsed type of CW modulation, is of the sync variety, that is having this shape here consisting of a main lobe and side lobes. This is a property that you see in any form of modulation in which the underlying modulation consists of things turning on and off. So when things turn on and off, you get something that looks like sync. And so that's what we see for Morse code, where this main lobe is just a few tens of hertz wide. And we also see it in pulse radar, where that main lobe is on the order of megahertz wide. An important consideration for any modulation is how it behaves in the presence of noise and interference. So for AM, we have some good news and some bad news. The bad news is that AM is vulnerable to interference. And what I mean by that is that if you have a carrier that looks like that, this is the RF waveform, and if you add to it an interference pulse, depicted in red here, then what you get is the sum of the waveform that you intended plus pulse. And since AM encodes information in amplitude, the interference becomes part of the message. So AM is vulnerable to interference because AM sends information in the form of magnitude. So that's bad news. The good news is that unlike almost all other modulations, there is no minimum signal-to-noise ratio for effective demodulation. That is, there is no signal-to-noise ratio at which AM suddenly stops working. A good ear, for example, can hear Morse code to signal-noise ratios much less than 1. That is much less than 0 dB. So if you need to operate at an extremely SNR limited scenario, and you're not really in a situation where interference is bothering you, then AM, and CW in particular, might be a pretty good choice. Now, granted, there are other ways to deal with this problem, but AM has the strength that there is no minimum signal-noise ratio. And that's in direct contrast to a modulation like FM, where we will see that FM does require a certain minimum signal-noise ratio in order to work properly. So an important distinction. So a few final comments. First, AM in any of the forms, double sideband, single sideband, CW, is very common, and it's not going away anytime soon. The applications I've mentioned are by and large applications which have been around for decades, and there's really no sign that they will be replaced with alternative systems anytime soon, because they work pretty well for the things they're doing. Now, there certainly are situations where some applications are transitioning from AM to digital types of modulation, but I would say that's a relatively slow process. AM is easy to demodulate. especially double sideband large carrier where you can do envelope detection. So a simple AM demodulator can consist of just a diode and a low-pass filter, and if you have the carrier present, as you do in large carrier AM modulations, that's all it takes. This is in contrast to FM and most digital modulations, where you need a more complicated receiver. So that simplicity of the receiver is a big plus for some applications. So overall, AM is favored for applications that require very small bandwidth, that is bandwidth on the order of the message signal, and good performance at very low signal-noise ratio. So these are both conditions that prevail in the lower frequency bands, VLF, LF, MF, HF, and the lower VHF bands. So we still see AM as a quite prevalent modulation at these lower frequencies where bandwidth is essential, that'd be very, very small, and good performance is required at low signal-noise ratio. So these are the reasons why AM is still around. That concludes this lecture.